So obviously I am talking about the open string. If I keep the ends of my open string fixed, which means I do not allow for the variation of x mu. The coordinate remains the same. So its time derivative vanishes. This is called as the Dirichlet. Boundary conditions. They are called as the Dirichlet boundary conditions. And how to make this thing vanish? We impose that x prime, we impose. So they are called as any arbitrary. So what happens here? Delta x mu is not 0. So x mu is not constant. So the end of the string can move around. Okay? The end of the string can move around. These are called as the Neumann boundary conditions. So here I have, for example, for a simple illustration, I have shown Neumann and Dirichlet boundary conditions, but you can have a mixture of the two. N, D, D, N. Okay. At one end you can have Neumann, at one end you can have Dirichlet, and so on. So whichever end you keep fixed, you impose Dirichlet boundary conditions. Okay. So x dot, its time derivative vanishes. Okay. And here, but this is not constant, this is not 0, but still I want the term times something. I want this thing to vanish. So I impose x prime mu equal to 0. This is the which means the space derivative of x mu vanishes. So the space derivative of x mu vanishes. Is this fine?
Yes. I was
Yes.
thinking it means that the endpoints are moving on the same. So sigma is constant.
In which one?
And
In which one?
I cannot.
No,
figure out
you only try to think like this. If the end of the string, if I'm holding the end of the string
Okay.
or not.
Mm.
Here I'm not holding, so the end can also move around. It can move around. It can go up or down, or it can move around in space. Here, the end is not allowed to move around. It has to remain fixed at the same point. So x mu does not change. And if it does not change, it gives me its delta of x mu 0 or time derivative, which is delta of x mu 0. Okay? So, and for the other kind of strings, the closed strings, in fact, a closed string has no boundary. A closed string itself is a boundary. For example, of a tube, the girls use these rubber loops for the hairs. This you take a tube and you cut them into thin slices. Each slice is a closed string, right? So the closed loop, we have to imagine that its width is 0. Okay, so the width of the string, there is no width. Okay, so 0 width. So a closed string itself is a boundary of some tube, and boundary of a boundary is 0, or in any case the same end, it comes back to itself. So you take periodic or anti-periodic boundary conditions. Okay. So and for the open strings you have either and D and D or D kind of boundary conditions. So, little bit about this. I thought it was the right moment to talk about this, and then we would also talk about this. Let me again create a space. Whatever I need, I should write again. But so now let me see which one should I take first. Should I go into the details of this first, or should I go into the Fermi mode, fermionic oscillators? And then we have to understand both of them. Let me briefly introduce the fermionic modes. Okay, let me briefly introduce the fermionic modes, and then where are my here. Yes. So let us try to understand. I still want to keep I still want to keep this here because it keeps reminding me that I have to do both of them. Okay, I mean I have to explain the features, and so I'm not trying to do that. I keep doing this thing alone or I keep doing this thing alone. I'm trying to put the things together so that we always have a clear perspective what is going on. All right, good. So a little bit on the fermionic oscillator. Okay. So the main point here is, before this, in the bosonic case, what are the main results for the bosonic case? We have in the first place, let me write it as AK and AL. Okay, this is just the notation. I'm just defining the notation. So I can alternatively either and similarly for the number operator K A equal to NK or NL Is this convention okay? So I can alternatively use any of them, either this or this, or this or this, or any of this, either here or as a subscript. Okay. Now, so the AK dagger is delta KL. AK here is 0. AK dagger Matthews, I'm just introducing the fermionic oscillator, okay? Because for this second fermionic part, we need to understand the fermionic oscillator and the fermionic modes, okay? Which would be, so that is just the idea, and this is just the convention that I could write A of K as either this or as this, either as subscript, okay? Similarly, A of L as A subscript L, and so on, okay? So then these are the properties of the standard properties of the bosonic oscillator that we have seen in the one-dimensional harmonic oscillator, right? We did this in details, and here NK.
Sorry, in the first bracket shouldn't there be a K and an L, not both K as in there?
Wait. So once again.
The first bracket where the delta KL turns out, it should be one K and one L.
Oh yes. Thank you. Thank you for the correction. Good, good. Please keep correcting me. Please keep correcting me. I'm likely to make slips here and there. Okay. So this n of k is a dagger k times a of k. Okay. And then one can easily prove that n of k, I can now, we have defined this, so we do not need this. Okay. And this, of course, harmonic. So now one can easily prove that n of k a of l, this is minus delta k l a of l, and n k a dagger l is plus delta k l a l dagger. Okay. So yes, and here what you do, you define the vacuum state for all k. This is in our standard bosonic oscillator, that you define the vacuum state to be annihilated by the annihilation operator a of k. For all k, this a of k gives you 0, and of course for